Hello everyone, this is Mohammad Asad Amin from Govt.Degree Boys College, Shah, Keamari. Today I am going to deliver you my fourth lecture on E by M for the electron by J.J Thomson method. I hope you will find this lecture interesting. Objective. In this lecture I am going to discuss with you that how we can calculate E by M value by using beam of charged particles in a uniform magnetic field. Introduction. J.J. Thomson was the first scientist who measured charge to mass ratio, that is E by M of an electron, when a narrow beam of charged particles are projected at constant speed v across a magnetic field in a direction perpendicular to the field. The beam of particles experiences a force which makes them move in a circular path. Principle. When a narrow beam of charged particles are projected at constant speed v across a magnetic field in a direction perpendicular to the field, the beam of particles experiences a force which makes them move in a circular path. What about the direction of the force? Since the force is given by the vector cross product of velocity and magnetic field, it is orthogonal to both of these. That is, the force vector will be perpendicular to the plane defined by the velocity and magnetic field vector. Now this is very simple, as you have studied at your first year level that the cross product rule says that curl your fingers of right hand from first vector in the direction of second through a smaller angle. The stretched thumb will give the direction of the third vector or a product vector. So here you see in the diagram, velocity is our first vector, magnetic field B is our second vector. They are at an angle theta. So applying the cross product rule, you will get the direction of the force perpendicular to the plane of velocity and magnetic field, which is given by an equation q v cross b. Now as you know that v cross b is equals to vb sin theta, so now we can write the magnitude of force as q vb sin theta. Now in the second diagram, if you are applying the right hand rule of cross product to determine the direction of a positive charge particle in a cross magnetic field, so it will be upward. And similarly, if you are applying the same rule on a negative charge particle, it will be downward. Now I will discuss with you about the motion of a charge particle in a uniform magnetic field. Suppose a positive charge particle Q enters into a uniform magnetic field B with a velocity v. So it experiences a magnetic force which can be determined more easily by the right hand rule called palm rule. Now according to the right hand palm rule, hold your right hand open, place your fingers in the direction of magnetic field B, place your thumb in the direction of velocity v. The direction of the force on a positive charge is directed out of your palm, which is towards the center of the circle in the first diagram, and this force is moving this charged particle in a circular path. Now if the charge is negative, the force is opposite, that is determined again by the right hand rule. Now in the second diagram you see that the velocity vector and the magnetic force vector are at an angle of 90 degree. So here we can calculate the work done on the particle by the magnetic force, which is 0. As you know that the work done equation is F dot S, where F is the force and S is the displacement. So its magnitude is Fs cos theta. Now if you put the angle theta 90 degree in this equation, you will get work done 0. Now because magnetic force always points towards the center of the circle, it changes only the direction of velocity and not its magnitude. It means that whenever a charged particle is moving in a uniform magnetic field, so its direction of velocity is always changing, but its magnitude, that is its speed, always remains constant, and this is one of the reasons that its path is circular. The rotation is counterclockwise for a positive charge, and for a negative charge the rotation would be clockwise. Construction. The J.J Thomson method consists of a highly evacuated glass tube fitted with electrodes. Electrons are produced by heating a tungsten filament electrically. Electrons are made to accelerate and form a beam by passing through a disc A and B. They are passed through electric and magnetic field. Finally, they fall on zinc sulfide screen. Working. Now look at the diagram which represents J.J Thomson tube, and actually electrons moving sideways are also directed towards the screen. By applying a negative potential on a hollow cylinder C open on both sides surrounding the filament, electrons are accelerated by applying a potential difference of above 1000 volt between the filament and the disc A. A further potential difference of 500 volt is applied between the disc A and B. The arrangement focuses the beam to the hole of the disc B, from where it is further proceeds to a straight line. When beam of electrons enters a magnetic field, it moves in a circular track. The force experienced by the electron is magnetic force equals to EVB, which is our equation number 1. Now in this equation, E is the charge on electron, V is the velocity of electron, and capital B represents the magnetic field of induction. The magnetic field provides necessary centripetal force to electrons so that it follows a circular path. So it means the magnetic force Fm is equals to the centripetal force Fc. Now according to equation number 1, magnetic force is EVB and the centripetal force equation is mv square upon r. Now r is the radius of the circular path and m is the mass of electron. So now v and v cancels on both sides, and on the left hand side we remain with EB, which is equals to mv upon r. Now shuffling this equation, for E by m we will get V by BR, which is our equation number 2. Radius of circular arc. The radius of circular arc in which the beam moves in the field region is determined. The radius is calculated from shift of the light spot from O to O dash, as you have seen in the diagram, which is given by r equals to b square upon 2a, whereas a is the distance between O and O dash, which is a relative shift of electron, and b is the distance between a screen and an electron gun. Now we will determine the velocity of the electron in the J.J Thomson tube by first method. The electrons are first accelerated by applying potential V between disk A and B before entering the magnetic field. Now the kinetic energy acquired by the electron is equals to voltage multiplied by charge. This is the basic definition of voltage or potential difference. It is energy or work done per unit charge, or kinetic energy is half mv square, which is equals to voltage multiplied by charge. Now velocity from this equation would be equals to bracket 2ve upon m to the power half. Putting the value of velocity in equation 2, that is E by m equals to V by BR, you will get the equation E by m equals to, now velocity in this equation replaced by 2ve upon m whole bracket power half divided by B into R. Squaring on both sides, you will get E square upon m square equals to 2ve upon m upon b square r square. Now E and E cancels on both sides and m cancels on both sides, so you will get E by m equals to 2ve upon b square r square. Now in this equation, V is voltage, E is charge of electron, capital B is magnetic field induction, R is the radius of the circular path. Now the second method for the velocity determination is called particle selector method. This is a more accurate method as compared to the above method. In this method, the beam is passed through cross electric and magnetic field. The electric field is so adjusted that the light spot comes back to O from O dash. That is, electron beam passes and straight without deflection. Now force on electron by electric field is given by an equation F electrical is equals to electric intensity multiplied by charge of electron. Now E by m is equals to V by BR, as we have derived this equation earlier. Now magnetic force is BeV. Since both forces balance each other, that is, when electron is deflected by the magnetic force, so we have adjusted the electric field in such a way that both the fields balances each other and the electron beam will go undeviated, or it moves in a straight line. Now magnetic force is equals to the electrical force. Magnetic force is BeV is equals to electrical force EE. Now in this equation, capital B is magnetic induction, E charge of electron, V velocity. Right hand side of equation, we are having capital E, which is electric field, and small e is charge of electron. Now E and E cancels on both sides, so the velocity equation is electric intensity divided by magnetic induction. As you know that E by m is equals to V upon BR. So when you put the value of this velocity, which is calculated by particle selector method, so you will get the value of E by m equals to E upon B upon BR. Now this capital B will multiply with capital B, so final equation is electric intensity divided by B square into R. After substituting all the values, that is the radius of the circular path, the magnetic field of induction, which can be calculated by an equation of Helmholtz coil, and the value of electric field, the E by m of an electron was calculated equal to 1.75888 multiplied by 10 raised to the power 11 coulomb per kilogram. I would like to say thanks to our Honorable Education Minister Said Ghani for giving us a platform to deliver our lectures to our beloved students. I would like to thanks to my principal Asghar Ali Channa and to all my faculty members. I also want to thanks to my son Sarif for giving me a technical support. Thank you so much.